Okay. Yeah, I think now it is being recorded. Okay. So, in this, brief presentation, I would like to discuss about video generation, more specifically video generation using diffusion models, right? Uh, to give a brief to understand a video diffusion, right? We'll have to have a decent knowledge of image diffusion. So I will briefly go. We'll discuss briefly about image diffusion, like for a couple of minutes, right? So the image diffusion that we actually need is a reverse diffusion. So reverse diffusion is, predicting an image from a noise, guided with the help of some, text, embedding, or, image based embedding. Like, let's say I want to create a dog, right? What, generally that we do is, you just give a text embedding along with, like,
So
yeah. So,
in the image diffusion process, there are two approaches, right? That's what you're referring to in the previous slide: forward diffusion process and reverse diffusion process, right?
right, right, forward diffusion and reverse diffusion. But, the actual diffusion that we like, generally talk about, right, is actually a reverse diffusion process,
Okay,
wherein, we try to generate the actual image, by trying to denoise the noise.
correct. But during the training, we will go through both, right? Forward and
Right,
reverse.
right,
So
right.
during the forward diffusion process, we kind of converting the signal to noise.
Yes,
And
we try to distort that, signal to a noise, and thereby learning that, a pattern.
got it. And that noise is a normal distribution.
Right.
Right. Yes.
Uh, Yeah, so I'll just go through a brief workflow of, how exactly image diffusion works, right? Like, we have an image noise and we have an embedding either from text or from an image. Let's say if you want to create a similar dog image, right?
Hmm.
We can extract this, that particular or relevant dog image as an embedding, and we can give that as an input. And we have, let's assume that, we have a unit that is already trained on large set of data. So what we can simply do is, we can simply predict the noise that can be removed from the assumed distribution. So what we'll do is, we take a sample from normal distribution and we try to uh, denoise that sample
Hmm.
to get the resultant image
Here,
in
you mean
multiple iteration.
when you say embedding, you mean like suppose for example in the text to image, so the embedding is the corresponding to the text, right?
Right. Right. If we have text as an input, this embedding refers to text embedding, or we can actually guide it through different process
Modality.
also, right?
Hmm.
So yeah, we can have an image, or like we can have a different, like, let's say there is control net, where we actually guide the generation using, like, let's say we can guide it using edges, or we can, guide it using semantic maps. So there are multiple ways that we can guide the diffusion.
Yeah,
So this
because
diffusion happens.
text to image, the
Right,
embedding is related to text. If it is image to image, then the embedding should come from the image portion of it. Suppose image
right,
in painting, more control editing.
right, right. So then the embedding comes from the image,
Got it.
right? Yeah. So given this embedding as an input, and, the latent vector that we sample from a normal distribution as an input to the pre-trained unit, what we try to do is, we try to predict the noise, and then we subtract the noise from the latent vector that we take. Let's say, x 1000 is the latent vector that we assume from a normal distribution, and this is a noise predicted. We subtract this noise to get the previous version, the denoised version of the latent image, right?
Mm.
And in the subsequent process, what we try to do, we take this x, 999 as an input, and we try to predict x 998 as an output. Similarly, and so on, we try to denoise. So let's say here, right, what we have is we have x2 as an input, and then we try to denoise this x2. So we predicted the noise that x2 could have, and we denoised it, like, and we subtracted it from x2 to get the x1. And finally, in the last step T0, what we are doing is we remove, like, we take this T1 as an input, and we predicted the noise that this T1 or like x1 has, and we subtracted it from x1 to get the x0. So this is the final image that we have. So what we essentially did in the whole process is we have taken a latent vector from a normal distribution, and through the help of a text embedding or like image embedding, what we have essentially done is we have denoised this latent vector to the image that we want. Right. So the video diffusion, right, is essentially is almost the same thing. Like, I'll go through a few examples, right? So I have so let's say if we want to create an image, right, we can give this time practicing karate. So this is an embedding. So this is an input that we have. We can maybe pass it, extract clip embedding out of it, and pass it through like a pre-trained diffusion network like this, like the text embedding that we have and the latent vector that we have, like together. Now we can predict this toad practicing karate image. Okay. Now, how is this helpful for a video? A video is essentially a sequence of frames, right, stacked together. So if you are talking about 1 second video, it essentially has 24 images. Like, if it's a 24 frames video, right? So let's say here, right, what in text guided image generation, what we have is we have text as an input, we have an image as an output. The same thing in text guided video generation, or like any guided video generation. In text guided video generation, essentially we have text as an input, video as an output. That means like we have stack of frames as a output instead of a single image.
So does it take okay, as we go ahead, we are going to discuss like how the temporal information can be fused into this one, right? Because the video has
right.
extra dimension.
Exactly. Yeah, so that's what we'll talk about in next, like in the coming slides. So these are just like examples of what we are actually going to talk about. Let's say if I want to generate text to some video, right, where like a puppy is walking in a park, right? So this is one example of I think from like make a video, I guess. So where you give this golden retriever puppy in the park autumn. So this is the video generated. Like more likely, like these are the frames that are generated. Yeah. So this is what we're talking about. So earlier we have a 2D as an output. Now what we have is like what we need is we need 3D as an output. When I say 3D, it means like we need to have stack of frames as an output.
But
So let's say if it's just
it's not simply stack, right? So there could be some kind of a temporal relationship, right?
yeah, there definitely has to be, like, else there is no temporal consistency, right? So that's what, like, we'll talk about how these temporal consistencies are actually being dealt with. So I'll give you a small example of, how these things are working. Let's say I have a latent distribution, right? Like it's normal distribution. And now what we are trying to do, we are trying to predict batch of images, right? This is one example that I've taken from this video earlier. So if you see, right, like, so in a general diffusion process, if you simply try to predict multiple images, right? Let's say if you are trying to, simply predict 16 images, obviously, at the end of a few iterations, what we are going to get is we are going to get different images, right? Like, so here, if you see one image is a cat, one image is a dragon, other image is a sunset, and so on, right? But this is without temporal fusion. Like if you just simply, take any T2I model, and if you try generating multiple images, this is what we are going to get. But let's say if we fuse this like temporal, if you fuse few things, right? If you fix few things in a way that, that then the data can be processed temporally, then we are going to get the actual like data that we want. So this is actually a network, LDM network, fixed after like fixed with temporal data, like temporal networks. So like I'll briefly go in, like, we'll briefly discuss how this is happening also. So I'll discuss a couple of works here. So one of the earlier work is make a video. So they have taken this because it has multiple aspects. Uh, so where it has a spatiotemporal decoder, it has frame interpolation, it has like spatiotemporal like super resolution, and it has spatial super resolution. Okay, so earlier, like imagine that we are generally dealing with T2A problem. What we are doing, what we will do is we have a image as we have text as an input, like a person doing yoga outdoor during a sunrise. What we'll do is we'll simply generate an image. But what we do here is right, instead of generating simple like a single image, what we are doing is we are generating multiple images like 24 frames. But what we will do is we will predict them at subsequent intervals. But how are these? But how is this possible? Like this is possible. Like I'll take a break here. I'll come to other parts later. We'll talk about spatiotemporal decoder like this. So imagine I have a image and I want to predict the output. Like I have a simple unit like that we use commonly in diffusion. Like let's say I have T2A network. I give this noise as an input and we predict the image as an output, right? Now to get a video, we need to simply stack the inputs like this. But the problem is we are not going to get the consistency in like over time, because the outputs that we are going to get right might not be even consistent. Like there can be dog sitting, one can be a dog standing, right?
So here, what
Now
about the
this is
temporal embedding? Here,
right,
timestamp.
right. Yes. That's where I'm coming, Praveen. So let's say, so this work, right, make a video is essentially an extension of, I think, stable diffusion, I guess. So
So here,
what they,
the video extension of the stable diffusion, right? The input is also a video and output is also a video, like a 3D stack, right?
right, right. So if you see here, right, like the network, what is the input? So if you are trying to predict an image, right, what we can simply do is we can simply predict like we can simply sample a normal distribution like B cross C cross H cross W. But what we are doing is we are sampling like B cross T cross C cross H cross W, where like
Mm.
T is the number of frames that we want.
Mm.
So I think this make a video predicts around 16 frames. Okay. Consequently.
That. So
So
it is a
what is
bit
the
of
difference
compute
that
intensive, right? It is because since everything is in the 3D space. Suppose if it is unit,
right?
it is 3D convolutions, 3D unit.
Yeah. So what exactly? So but the thing is right here, these people have done like pseudo 3D convolution, like
Uh,
how we use a con 2D transpose we have, right,
it is
instead of
like a separable in terms of 2D and 1D.
exactly like separable convolution, right? Here we have another layer added in between the existing pre-trained networks, like like in between existing let's say in this architecture, right? In between existing cross attention network, what we are adding is we are adding both spatio and temporal like consistent networks that can make this network consistent. So in this particular work, right, what we are doing is
Can we put it this way? Like since we are extending the stable diffusion to 3D, so in order to make it compute like bit easier, so we are trying to decompose 3D into 2D separable, a product of 2D 1D. So 1D is the along the temporal dimension, and since
right,
it is decomposed into 2D 1D, the 2D is coming from the pre-trained image weights.
right, right,
Oh.
right. The same thing. So 2D is coming from pre-trained weights, okay, that we have, and 1D con, right, that we are doing. So these the networks that we are adding 1D con, which is a temporal network.
Along the
Let's
temporal
say,
dimension.
yeah. So it operates across this T,
Hmm.
right? And after that, following that, we have added another 2D attention network. So because 3D attention is very computationally expensive, right? Even like it is computational as well as memory expensive. Right? In terms of memory also it is expensive, right? So again, here we are adding pseudo 3D attention. So we have a 2D attention like in terms of spatial dimension, like across space, and we also have 1D attention that spans across time.
Since it involves same convolutions, so again they are trying to decompose into 2D 1D, and they are trying to initialize the 2D attention from the pre-trained 2D stable diffusion thing.
Right. Like so this is actually what we are doing, right? We are not building any network from scratch. What we are simply doing is we are simply using existing network, and we are adding these layers as an intermediate networks.
But they should learn 1D attention and 1D convo, right?
Yeah,
On the
1D
video
attention,
data set.
1D attention. Yes.
So in
Yes.
a
So
way,
what we'll do is we will fine tune them. We will fine tune with videos.
Got it. So the additional introduced layers are fine tuned with the help of video data set.
Right. So if you see here, right, like if I added here, so we have existing temporal like 2D convolutions. On top of it, what we are doing is we are adding a temporal dimension. It like we are adding 1D convolution that spans across temporal dimension. So after that, we have a spatial attention map, and after that, like the output of the projection of the spatial attention map is fed to temporal attention.
Got it.
Okay. So then how is this training? How is this being trained? One thing is the text to image network that we have, right, is already trained on like like lot of data. So we are going to use it. So we take a pre-trained model and we'll fine tune it on video data. There, yeah, and like so there is like whole lot of topic on how the data is being curated. I haven't added in this presentation. Maybe for this next presentation, we can discuss on how this video data, right, is actually being sampled.
Okay. Do we have
So
any
there are
video data sources like
yeah, so there are a couple of sources. LVD, there is one data set, large video data set, and there is this WebM video data set, and a
Web to
couple
video?
of data sets. No, I think I have mentioned it here somewhere, like web video. Let me see. Yeah, WebVid. Yeah, WebVid 10M is one data set that we have, and LVD is one data set. LVD is like large data set.
Okay. No worries. Actually, as and when we reach to that slide, we can point out.
Yeah. My screen sharing is paused.
I think you should go back and
You're able to see my screen?
no, it's a blank. You reached the end of the slideshow, so you exit it and again start. Just the slides only. Close the slides and open it again. Now fine.
Okay. Okay. Now, what we've discussed is we have discussed essentially this spatial like temporal decoder part. So what we are actually doing, right, is we are predicting. We're not actually predicting actual duration. Let's say if you want to generate 80 frame video, right? Like 80 frame, if we actually discuss it in terms of 16 FPS, right? It's hardly 5 seconds. So what we do is we try to predict frames with 5 frames interval, like zero. We are predicting 0th frame, we are predicting 5th frame, we are predicting 10th frame, so on. We'll predict till 80. Then what we'll do is we'll try to do a frame interpolation between this frame. Then what we'll do is this frame interpolation process is followed by this spatial temporal super resolution, so that you do not have any inconsistencies. Then it is followed by spatial super resolution to make it a full-fledged view. So this is how the most of the initial works started dealing with this problem. So the architecture and the way they would train it, would differ, but more or less, a lot of people have followed similar strategies. Like, you have keyframes where, like, so here keyframes are like 0, 5, 10, right? So you have keyframes, you try to like, interpolate them, and then you try to enhance them to get the higher resolution. But if you see, right, there are few challenges to this work that, yeah. So what are the limitations? The limitation is like very less global consistency, because what we are doing is we are predicting 0th frame, 5th frame, 10th frame, like, 15th frame, right? Uh, we uh, like during training also we do not have complete we are seeing only these frames, right? 0, 5, 15. So there is very less global consistency, and the length of generated clip is very less. It's hardly 80 frames. Okay. And also this is not a single stage network. It's a multi-stage network where we have multiple, like, things, right? Like we have keyframe generation, we have, like, spatial temporal superposition, and we have spatial superposition networks in place.
So those
Uh,
are the post processing, right? Suppose if we generate a 16 FPS video in order to make it to like high FPS, so that is the post processing steps, right?
right.
Oh,
Right. So in general, so this works generate, like, 16 to 30 frames.
16 to 30 frames.
This, yeah, make a video. So this is old work. This is almost around 2 years back.
Okay. So
Now,
when you say
right,
less global consistency, so do you mean the temporal consistency, lacking in a
right.
temporal consistency?
Yes, the temporal consistency is lacking. What, because what we are essentially doing here, right? We are merely interpolating,
Hmm.
which might or might not actually predict the actual flow of what has happened.
That.
Right? Like, let's say if you're throwing or, let's talk about high, like, high FPS, right?
Hmm.
Where the object is actually moving very fast.
Hmm.
Then what happens is between frame 0 and frame 5, there could be a lot of variation, right? Like if it's a normal, like the way a normal walk, and let's say if you are trying to, recreate Usain Bolt, things would differ a lot, right?
Hmm.
The frame interpolation network has to play, like bit consistency, like has to impart consistency also. So
Got
that
it.
feature is lacking.
Correct. So if I want to summarize it, so in a way, through network, we are learning the coarse temporal information, but to get to the finer temporal information, we are trying to do kind of a post-processing. So because of that one, there is a temporal inconsistency because it's not the temporal finer details are not learnt. It is kind of we are extrapolating through the available information, right?
Right, right.
Right.
Yeah. So there is one work that I want to discuss. Before that, I would like to talk about, one different architecture, space-time unit. So this is bit different from this, unit that we talked about earlier, where what we are doing there is, in between frames, so we are attaching both. So if you see this architecture, right? So what we have is we have both, spatial convolution as well as, temporal convolution, spatial attention as well as temporal attention, right? So this ST unit differs like differs a bit. So this ST unit is actually an extension of Imagine network. So Imagine is again, like, text to image, like, foundation model. So they have modified this Luminaire. These people have modified that work so that, you can generate videos. So there are two types of, blocks that these people have added. So they call it as convolution based, inflation block. So if you see here, right, on the right hand side, what they have done is for a spatial layer, like for the existing layer, what they have done, they have added a 2D convolution. They have added, a norm layer and activation layer, and they have added 1D convolution, again norm layer and activation. and a linear projection. And there's a skip connection to the existing pre-trained spatial layer.
So still these guys also explore those pseudo convolutions only, right?
Right, right. If you see here, right, they're using sort of because 3D convolution is very expensive.
Correct. So how
And
these guys are different
instead
when
of
it comes
yeah,
to
instead of adding attention to every block, right, what they've added is they have added attention only to the bottom layers.
okay, so where it is not computationally
Where the
intensive.
info yes, yes. And
Yes.
there also, if you see, right, they have a pre-trained spatial layer and they've added 1D convolution, 1D attention, along with a linear projection.
Okay, so they have applied only attention on the bottleneck layer.
Right.
Okay, not bottleneck, but on the low
But not
resolution part.
in the in the very high, very high level features, like I mean like very low level features, uh, they're trying to do attention.
Okay.
Okay. So like the one advantage of this is like they are able to generate uh, like large number of images at once, and like this space-time unit is comparatively faster than the existing like the previous one, right? So I have given like a small example of how this like how this network is affecting the existing network. Like let's say given this 3 frames, right, of 100 cross 100 image. Let's say you have 16 layer, like 16 filters for 2D convolution. This is what is happening. Like for after 2D convolution, you have this 3 cross 16 cross 8 cross W. After 1D convolution, let's say you have like 32 filters. So it is going to become 32 cross 100 cross 100. Let's say after linear projection, like to make it to make it match with existing spatial network, right? If the filters are like 64, it is going to become 64 cross 100 cross 100. So this is one of the like I just wanted to show how this network, how this specific inflation block is working. Oh, so to summarize, what they are actually doing is they have added this like let's say this 5 layers to the existing image network, and similarly they've added this particular 2 layers to the attention like attention network that Imagine already has, and they have followed the same procedure
So
like
this
and they have fine-tuned.
attention-based inflation block is only at the bottleneck, right? Or is
Right.
it everywhere?
No, it is only the bottleneck.
Okay, okay. So in the initial layers, it is a simple 3D convolutional blocks only, in a way, if I want to put it.
Yeah, initial is simple 3D, like pseudo 3D.
Pseudo 3D convolutions. But there is no attention
Right,
on the low level features. There is only attention on the bottleneck, which is much higher level features.
right. Okay. Yeah. So yeah, I want to talk about this Lumiere. Okay. So the general approaches of general temporal superposition models, like temporal superposition model is like the one that we have discussed earlier, where we have what we'll do is we'll essentially predict T0, T5, T10, like so on, T15, so on, so on, and we try to interpolate, right? This is exactly like the same thing that happens in general model. So we predict keyframes, right? And what we'll try to do, we'll try to do a temporal super resolution, and then we try to do a spatial super resolution to get the video. Okay. Now, how is Lumiere different? Lumiere is different because it tries to predict this. So Lumiere is different because it tries to predict this whole 80 frames at once. So here, right, what these people have done is, so this is possible with the help of ST unit. We are directly predicting all the 80 frames, and these 80 frames are directly processed with a spatial super resolution. So now we don't need to have this temporal super resolution because we are not doing any interpolation or we are not doing any frame interpolation here.
Okay,
So we
this is when you say our approach. So which one you are referring to? Paper? Which
so our approach in sense, sorry, like I'm actually like referring to Lumiere.
Lumiere? Okay. So they which one is using the TSR followed by SSR?
So make a video initial, the one
Make
that we've discussed earlier, right?
okay,
So we predict keyframes and then we interpolate it
got it,
using this frame interpolation. Then we do temporal super resolution, spatial super resolution, so on.
got it. The post processing which we were discussing.
Yes, this one,
Got it, got it. Yeah.
right? And yeah, so this Lumiere approach is different because it is predicting all frames at once. So here there is no need of interpolation. This work can actually uh, like generate very intricate videos with high complexity as well, with like minute details in motion. Also, it can predict good.
So, like, is it computationally intensive or how it is overcoming that challenge? That because if they want to adapt it to the high FPS videos, so how they are trying to adapt
So
it?
one, yeah, from what I think is like that this architecture is completely different from the earlier architecture that people have used, right? So
Mm.
they've used images. Uh, so I think this is relatively computationally not very expensive. So
Okay,
that is why
so
they're able to do that.
the architecture supports that kind of process in a more computationally less intensive way.
Right.
Got it.
I think so. And one thing that they have done is they have used something called as multi-diffusion. So this is a whole different topic on itself. Maybe like for the next discussion, right?
Mm.
We can discuss about this multi-diffusion. This is very interesting because what they've done is, so if you try to denoise again these images, right, separately, then there is a chance that because this again spatial super resolution models, right, are based on diffusion. If you try to like denoise these images individually, there is a probability that there can be inconsistency somewhere.
Sure, sure. We
Maybe the
can.
color panda color white can become red or purple. There can be a high like bit of chance, right? So
Sure.
that they are able to overcome it through this technique called as multi-diffusion.
Got
So these are few examples that you know that are the outputs of this Lumiere, where yeah, I mean like we can find like a lot of these videos like in YouTube. These are data sets that I found currently WebWid 10M and LVD. So they
so.
are like
Are
other
these datasets available like free or
WebWid 10M I think is available openly. So
okay?
LVD I'm not sure. I have to check. But
That
this can be curated. So there is one paper called as Stable Video Diffusion where they have explained exactly how to curate your own data set for these video tasks.
okay, great.
Right? So this is overall introduction of how this video diffusion in general works. So maybe for this next version, right, we can actually discuss on what are the evaluation techniques and how is the training happening exactly. Like we've just discussed on like overall architecture, right? Like
That
basically we have discussed only this blocks of what is happening. Maybe in
so.
next iteration we can
Uh,
discuss on
yeah. So
what
if I
exactly is
want,
happening.
so if I want to summarize, basically out of this one, the takeaways. So the important works are first they are adapting the existing 2D stable diffusion, that is the text to image one, to the 3D. That is a video thing, and after that the improvement is the StuNet, and after that it is a Lumiere. These are the main works, right?
Right, right. So there are a lot of works. I have taken this because there are like two different works that I wanted to discuss.
Okay, sure. Right, right.
Yeah,
Great, great.
right.
Thanks,
Yeah, I
I.
think with
Yeah,
this
yeah,
I
yeah,
will close my discussion.
sure. Thanks. Thanks,
Yeah,
I.
thank
Bye.
you. Yeah.